Hello everyone, my name is Kai. In this talk, I'm going to introduce different types of graph Laplacian matrices and explain how we can use them to connect the dots of different cooperative control problems in multi-agent systems. This is part 3, the last part of this talk. We have previously introduced the standard type Laplacian and see how it was used to establish rendezvous and consensus of multi-agent systems. And then in part 2, previous one, we introduced complex Laplacian and we used it to establish what's called a similar formation. And in this last part, we're going to further look at another type of formation control called affine formations, and we will use what's called signed Laplacian in this part to establish affine formation control. In the previous part 2, at the end, we discussed whether or not we can scale the formation with different ratios along different axes. We may want to do so in order to efficiently navigate the formation through some tunnels created by the obstacles in the environment. And this is not possible with similar formation, because if we look at the definition of the similar formation as a complex linear combination of two vectors, the vector of 1 and the vector of the target configuration, which is a complex vector, there is only one scaling ratio rho, which is applied to the whole target configuration. So with similar formation, we cannot scale the formation with different ratios. Only one scaling ratio rho is available. Obviously, in order to scale them differently along different axes, we need two scaling ratios, which can be independently applied to different axes. For that purpose, let's represent the 2D space as a 2D plane, not as the complex plane anymore. So we are going to write each point in the 2D space not as a complex number anymore, but as the two-dimensional real vector. So if we are still talking about a pentagon shape as the desired shape, we can translate the previous complex target configuration vector, which is a 5-dimensional complex vector, into this 10-dimensional real vector, because we can write each point, each specified point for the target configuration as a 2-dimensional real vector, as we have done here. Then we can define a affine formation, C prime, which is a formation that can be obtained from the target configuration through, again, a translation and a rotation. But if we add this scaling matrix, which is a diagonal matrix, the diagonal entries contain two different ratios, rho 1 and rho 2, that can be applied separately to two axes. And with this, we can scale the formation differently along different axes. Now let me add one more rotation matrix, this one, to the left of the scaling matrix. This addition doesn't really change the allowed transformations. The allowed transformations are still translation, rotation, and the scalings, now different scaling ratios on different axes. But with this addition, we can write this C prime in this form, which is the affine form of the target configuration vector C. And that's exactly why this C prime is called a affine formation, and that's how the name comes from. Also note that this rotation matrix U, scaling matrix gamma, and the rotation matrix V constitute what's called the singular value decomposition of the A matrix here. So the two different scaling ratios correspond to the two singular values of the matrix A. Then the affine formation control problem is to design distributed control UI such that it doesn't matter where the agent starts, they always converge to a formation that can be obtained from the impose target configuration by translation A, rotations U and V, and scalings rho 1, rho 2, to different scaling ratios that can be applied to two different axes. Now we can define this set of all possible affine formations by plugging in the definition of the affine formation Xi prime. So we can restate the problem as requiring the state to convert to a point in the set. Now for distributed control UI, it takes exactly the same form as we used in a similar formation in the previous part 2, except that everything here is either a real number or a real two-dimensional real vector. In particular, this epsilon I is a non-zero real number, and aij is also a non-zero real number that should satisfy this linear equation, which is a real linear equation involving the two-dimensional relative positions of the agents in the target configuration. And the purpose of satisfying these linear equations is again to encode the target configuration into the kernel of the Laplacian matrix. So if we plug in this UI back to the dynamic equation, this is what we get. We get this compact x dot equals minus E times L. We had that in the similar formation case. But here we have chronic product I2. Why so? Because now we are dealing with two-dimensional real space. So that gives rise to this chronic product I2 and times X. E is a diagonal matrix whose diagonals are the epsilons. Since the epsilons are non-zero real numbers, so E is invertible. And L is the signed Laplacian. And we have L chronic product I2 times Xi is 0, thanks to these linear equations. When we stack them together, that's the equation we get. That means that our target configuration lies in the kernel of the signed Laplacian chronic product I2. So if we view that target configuration vector axis by axis, we can see that the Xi can be separated into two vectors along two different axes. Those two lie within the kernel of the signed Laplacian L. Moreover, we have the kernel of L chronic product I2 contains the set of all affine formations. To verify this, we will take an arbitrary point, namely a affine formation, an arbitrary affine formation from the set script A of Xi, and then verify that that arbitrary taken affine formation lies in the kernel of L chronic product I2. Namely, we use L chronic product I2 times a Xi prime, which is an arbitrary element from the set script A. And with simple calculations, we can verify this is the case. This means that the kernel of the signed Laplacian chronic product I2 contains all possible similar formations. And also the rank of the signed Laplacian is no more than n-3. Well, that means that the kernel of the signed Laplacian is at least 3 dimensions. Which 3 vectors? We know 1, of course, by definition. That's the vector of all ones. And from L chronic product I2 times Xi equals 0, we have already mentioned that when we view that epsilon axis by axis, we actually have 2 corresponding different axes Xi. If we call the Xi one axis, Xi the other axis, those 2 vectors lie within also the kernel of the signed Laplacian. So the kernel of the signed Laplacian is at least 3 dimensions. On the other hand, here is the counterpart result for the rank property of signed Laplacians. Specifically, the rank of the signed Laplacian is lower bounded by n-3 if the graph G contains a spanning 3 tree. A spanning 3 tree is a subgraph with 3 roots, and all the other nodes can still be reached from one of the 3 roots, even if we remove 2 arbitrary nodes in the graph. For example, here in this graph, we have nodes 1, 2, 3 are the 3 roots, and let's take node 4 as an example. Let's say we remove nodes 1 and 2. 4 can still be reached from root 3, obviously. Let's say if we take out the 2 and 3, then 4 can still be reached from root 1 via node 5. Let's say if we take out the 2 nodes 1 and 5, let's say, well, 4 can still be reached from either 2 or 3. And it can be verified that the node 4 indeed satisfies this condition, and in fact node 5 satisfies the same condition as well, and this graph contains a spanning 3 tree. Now let's make this graphical assumption. We assume the graph contains a spanning 3 tree, which means that the rank of the signed Laplacian is at least n-3. So this leaves only one possibility, namely the rank of the signed Laplacian is exactly n-3. So the kernel of the signed Laplacian is exactly 3 dimensions. And in this case, the kernel of L chronic product I2 is exactly the set of all affine formations. And that's exactly what we want, because again, we will use a strategy of driving the states toward the kernel of L chronic product I2, which we will reach a affine formation. So for the overall system, if we can design the diagonal invertible matrix E such that the n-3 non-zero eigenvalues of minus EL are stable, namely having negative real parts, then the state will convert to the kernel of minus E times L chronic product I2. Because E is invertible, that kernel is the same as the kernel of L chronic product I2, which is the same as the set of all possible affine formations. That means that the state will convert to a affine formation. To design the real weights Aij to satisfy a linear equation so as to encode the target configuration into the kernel of L chronic product I2, that amounts to solve a system of linear equations. Let's take an example. Let's consider node 4, whose 3 neighbors are 2, 3, and 5. So the corresponding equation is this one. How many equations are here? Well, because these Xi's are 2 dimensions, so we have 2 equations here. How many unknowns? Well, we have 3 unknowns, 3 ways to be designed. So 2 equations, 3 unknowns, infinite solutions. Therefore, we know that with 3 neighbors, this is always doable. And finally, we just need to set the diagonal entry of the signed Laplacian to set that row sum to be 0. And we can do for node 5 exactly the same way. And this is the resulting signed Laplacian. We can verify that every row sums up to 0, so 1 is in the kernel of L. And we can also verify that the L chronic product I2 times the target configuration, which is this one, it's a regular pentagon, is 0. And if we view this target configuration axis by axis, if we denote those by Cx and Cy, then in fact we have L times Cx equals 0, L times Cy equals 0. So 1, Cx, Cy are the 3 vectors lying inside the kernel of the signed Laplacian. However, the eigenvalues of minus L are not stable. In fact, in this case, we have 3 zeros, but the non-zero eigenvalues are both unstable. So we need to design a invertible diagonal matrix E to stabilize minus L. And here's one solution that does the job. So with this pattern of eigenvalues, we should expect a affine formation. Indeed, we have it. Starting from a given initial condition, the agents convert to a 5-gon shape. In this case, the horizontal scaling ratio is larger than the vertical scaling ratio. And here's our solution to the affine formation control problem. With this form of distributed control, we can solve the affine formation control problem under these two conditions. One, the graph contains a spanning 3 tree. Two, the target configuration is generic. We can also easily manipulate the entire affine formation by controlling only the 3 roots. Let's say the initial scaling ratios are rho 1 is equal to 1. That's the horizontal ratio. Rho 2, the vertical ratio is 0.5. We can move the third right root up so that we can increase the vertical ratio to 2, and thereby we stretch the entire formation vertically. We can also keep that ratio, but rotate and translate the 3 roots so as to rotate and translate the entire formation. We can also adjust the relative positions of the 3 roots so that both ratios, both the horizontal and the vertical ratios, are the same. By this, we can see that affine formations include similar formations as a special case. Now let's recap. In this 3-part talk, we have introduced 3 different types of graph Laplacian matrices. They have the same definition, but their difference comes from the nature of the entries. There is the standard Laplacian, the complex Laplacian, and the signed Laplacian. And we have explained how to use them to solve multi-agent cooperative control problems from consensus to similar formation and affine formation. There are many more related multi-agent cooperative control problems that I have not covered, but every one of them relies critically on these algebraic rank conditions and the corresponding graphical conditions that are covered in this talk. If you want to read more details and for some further readings on cooperative control problems in multi-agent systems, please check out our recent book on directed cooperation of multi-agent systems. And with that, thank you very much and see you next time.